Hi guys, today we're going to talk about why memory nodes is a bad idea in behavior trees. And the problem is that some implementation lack memoryless sequences. They only have memory nodes. And what can we do about that? So, what is a memory node? Well, a normal memoryless sequence node ticks next child if the previous one returns success right now. So it's constantly checking if the previous one returns success, and when it does, it ticks the next, and so on. A memory sequence node, on the other hand, ticks the first child that has not yet returned success. So it remembers what subset of the children that have already returned success, and then it ticks the next one that has the first one that has not returned success. So what is the difference? So let's look at this simple example. We have a robot that is supposed to visit points A, B, and C in that order. So first A, then B, and then C. So a simple design, and this is I think why the memory sequence was created, that you can do this simple design to solve this problem. You go to A, you go to B, you go to C, and then you remember when they succeeded. So first you go to A, and when A returns success, you go to B, and then going to B, you realize you're not going to be close to A anymore. So go to A. A might not return success, but you remember that you already kind of did this, so you keep going to B and so on. So if this was not the memory node, you would get into trouble here going to B, because then going to A would not return success when you're not close to A, and then you would kind of get stuck in between A and B, toggling between these actions. So the fix, having a memoryless sequence node, is obviously this. You add this subtree where you check if you already visited A. If so, you go on to the next subtree. If you didn't visit A so far, you go to A, and then at some point A is going to be visited, and then you check if B is visited. If yes, you check if C is visited. If no, you go to C, and so on. So this is slightly more complex. So this is, I think, why they created the memory sequence node, but you lose reactivity, as we're going to see shortly. And in both cases, you need memory. So either you have the memory in the node here, or you have the memory in the conditions here, remembering if A and B and C was visited, obviously checking some kind of variable where you store this knowledge. So as I said, the problems with the memory sequence node appears when you want a reactive behavior. So for instance, reacting to fire. So in case of fire, we want to leave the building. That's a reasonable thing to do. So if a fire occurs here, there's a fire alarm going off, and then we want to stop visiting these positions, instead leaving the building. And the fix up here is fairly straightforward. You just add to the left here a check of the fire alarm and evacuating the building if the fire alarm is indeed on. So if we're safe from fire, we go on to visit the points. If we're not safe from fire, we exit the building. So fixing this tree is not as straightforward. So let's look at an example using Panda BT. So we're going to have this example where basically this robot is going to visit points A, points B, and point C in order. If the fire alarm goes off, there's going to be a red lamp blinking over here, and then we want to exit the building through here. We're going to try first the kind of the standard sequence design as we saw here, which is also this BT1. Here, as you can see, this is the same as this guy. If you're safe from fire, you get outside. Safe from fire, if you're not safe from fires, you get outside. So it's not safe from. If safe from fire does not return success, we exit the building. If it does return success, we check if A is visited. is visited A. If that's not the case, we go to A and so on. And then we're going to have this design with the standard sequence node here, and then we added the same kind of fix for fire here to the left, and we're going to see that that is not working too well. So this BT is down here, and this is the root up here. We're going to swap between which of these subtrees we're going to be using and comment the other one. Furthermore, we're going to do this switching between the memoryless sequence and the memory sequence by ticking this box, remove memory, which basically does this in the code. So if remove memory, we're going to reset the BT. So this Panda BT has memory by default, but if we reset it each tick, it's going to work like a normal memoryless node. And then the fire alarm, we're going to tick that on and off just to illustrate what happens. And then the alarm is going to run, and this safe from fire, when there is a fire, safe from fire is not going to return success. So that's it. So let's see what happens when we run this. The robot first moves to point A, and when A is visited, it goes to point B, and when B is visited, now it goes on to point C. And now all the points are going to be visited, and the whole tree returns success. No problems with fire. Now let's add the fire thingy. We restart the whole simulation, and now we invoke the fire alarm, the robot exits, we turn off the fire alarm, the robot goes on to point A. Because right now it's safe from fire. We're going to turn on the fire alarm again, the robot runs, turn it off, the robot continues to visit point B. Point B is soon going to be visited, we turn on the alarm, turn off the alarm, and the robot goes on to point C. The kind of reactive behavior we wanted. And again, at the end, the whole BT returns success. So now we're going to try the same thing with the other design. This design here. Here you see first, now we're stuck between go to A and go to B because we're still in the memoryless design. So now we're gonna use the memory. So now it works. We get to A, and when this returns success, we go to B. When this returns success, we go to C. And here you can see actually a little feature of this implementation is that it resets when we have achieved all the ABC goals. Now the fire alarm is on, the robot is ignoring it, it thinks it's still safe from fire since the last time we checked it was safe from fire. And only when we visited all 3 points, it actually rechecks if we are safe from fire and evacuates. And when we turn the alarm off, it still thinks it's not safe from fire and waits outside the building. So this is an example of the memory node not working as well as we would have wished if we need reactive behavior, not just going from A to B to C, but under influence of external events and then having to react to those. So what kind of memories do we have in a BT normally? Should we use a memory in the BT in the form of these memory sequences, or should we try to put our memory in the blackboard together with the rest of the knowledge? Well, a common solution is to have a blackboard. So this is some example from the net. There we have a blackboard that holds variables and values relevant to the AI of an agent. So in this case, it's some kind of action agent here. So you want to keep track of its own health, its armor, its partner, its destination, and the closest cover, and so on. And this is reasonable. So most agents do need some kind of memory and cannot rely on current sensing of data alone. So it would be a bit stupid. So you need to know basically what's in your pocket. If you put something in your pocket, you can't sense it, but you need to have knowledge. Remember that, or the agent would appear to be very stupid. Also, if you just enter the room from another room, it's kind of stupid not to have some knowledge of the other room, and so on. And in most instances, having some kind of map for navigation, keeping track of important object locations such as your destination, the closest cover, and so on, makes sense. So we do need memory somewhere. And the argument of having the memory in the BT might be that you can do without other types of memory, but you need a lot of memory, knowledge, and so on. And then the question is, does it really make sense to also have memories inside the BT, or should we also push that kind of knowledge onto the blackboard and check it with conditions? And I think that the later thing actually makes sense, to not use the memory nodes. So you should also keep track of your tasks. And it makes sense to collect knowledge and beliefs on a blackboard, kind of like this. And as we saw before, reactivity is good when the outer world changes without your doing anything. So for instance, a fire starts, or some other agent is moving stuff around, and so on. So reactivity is normally in an AI is normally described as where the response depends on the current state of the world only, no dependence on previous states, which is kind of similar to the Markov property. Reactivity is good in an AI since it makes it easy to predict and understand its actions. It only depends on what the current world looks like, and not about kind of the complete history of the world. Having a blackboard in some sense depends on previous states, and especially in examples like this, where you have A is visited, you can't really see by looking at the scene that A has been visited, or if it has not been visited. So in that sense, you kind of reduce reactivity, but you can also argue that the blackboard is part of the current state of the world. Normally, you would have visit A and B to actually do something, and then the world kind of changed, or you just checked that there was no bad guys or something at point A. Either way, you can argue that this is actually part of the world state. So if you include the blackboard in the current state of the world, you still have a reactive agent with designs like this, even having access to variables. So it's overall, it's reasonable to take action based on sensor data and your beliefs and your knowledge about the world. So basically having a blackboard and having a memory. So you might wonder, why are we talking about this? Isn't this obvious? Well, we're going to see in the next slide that there are some aspects of this that might be important. So you might think about expressiveness of an algorithm, or a behavior tree in this case. So can more be done using memory nodes than just using non-memory nodes? Well, the short answer is no. So this was investigated in a paper by Biggar, Zamani, and Shames, our Australian friends. And the key result summarizes the main result of the paper is as follows: that now they have these definitions of the PBT, the MBT, and the UBT. It basically stands for the pure BT, no extra variables, no memory, and no blackboard. So that is actually less expressive than the MBT, which is the memory node BT, which in turn is less expressive than the UBT, the unrestricted BT with extra variables with a blackboard. So the previous slide was to argue that this actually makes sense to have extra variables. And if you agree that this makes sense, there's no kind of benefit from expressiveness point of view to use memory nodes, because only memory nodes is less expressive than the unrestricted BT. So basically, BTs with access to extra variables, blackboards, which we argued kind of makes sense, can implement any action selection mechanism that memory nodes can. And that is the definition of expressiveness, so it's more expressive. So from a theoretical point of view, there's no need to add the memory nodes. And from a practical point of view, I would say there's also no need to use them. So how do we create non-memory sequences if the tool we're using has a default of memory sequences? Well, as we saw in the Panda BT, what we could do is do a reset to remove the memory, and do that every time step of the simulation in the update method. If we're using PyTrees, which is another good library, Panda BT is very nice in my point of view for use in Unity. PyTrees is a Python implementation that is can be used in many places. Then there's a parameter on the sequence node that is defaulted to memory true, but you can set that to false and get a non-memory sequence. If those options are not available, there's a more kind of intricate way of using inverters and non-memory fallbacks to create a non-memory sequence. So this huge block here, sequence, actually hides some details of how you can create that non-memory sequence. And the details are as follows. You have a bunch of inverters and a non-memory fallback. So, and it works like this. So if a child returns success, the inverter inverts that to a failure. The fallback, getting a failure, that ticks the next node, and so on. And that is actually, imagine this is a non-memory sequence. So if you have success from your first child, then you tick the next. That's what you want the sequence to do. In the other case, if you have failure from your first child, then you want the sequence to also return failure. So the failure is then inverted to a success. The fallback is happy with just one success from any child. So given a success here, the fallback is going to return success. And then the inverter is going to invert that to a failure. So overall, if the first child fails, the sequence here is going to return failure, which is also what we want. And running is just progressed through the node and all the inverters being just a running. So that also works as we want. So this way you can create a non-memory fallback from inverters and you can create a non-memory sequence by using non-memory fallbacks and inverters. So, to summarize this short video, reactivity is good to handle cases like the fire alarm and other agents doing stuff that you need to react to. It's good. It's a good kind of design rule of thumb to have response depend only on the current state. So no memory nodes. I think it becomes harder to read if you add the memory nodes. Makes it easy to predict and understand what your agent is doing. But memory nodes obviously make sense in terms of keeping track of your belief of the world and your knowledge of the world. So therefore, I think it makes sense to view these as part of the world state and then have a reactive agent reacting to not only what you sense, but also what you know and believe. There are many new methods and research results use the reactivity of behavior trees. and the non-memory sequences are crucial for taking advantage of this. Research results regarding safety guarantees, convergence guarantees, and so on use this. So it's important to have them in your tool set. If you want to see examples of that, you can check other videos and also research papers by different researchers in the field. So make sure your BT software includes non-memory sequence. This is the sequences, that's a take-home message. And I would advise you to avoid the memory nodes. But obviously, you can choose your own path in the pursuit of happiness. Thank you for watching, and if you want to know more about behavior trees, you can check out our book that is available for free on archive. There's a bunch of other videos on YouTube, and if you want to use a Python implementation, I suggest you use PyTrees, but remember to use the memory setting of false to get the memory-less sequence, or use PandaBT if you're working with Unity 3D, and then remember to reset the tree at every time step. That's it. Bye.